All right, hello everyone. My name is Jason Scholes. I'm the CEO for Trusted Autonomous Systems Defence CRC, and just admitting a few more people here coming in. Simon Ung would normally be your host for this today, but he's otherwise busy and couldn't make it, so I'm taking up the role. I'm new to using Zoom as a host mode, so bear with me, but I think we should be okay. All right, so we have a couple of really exciting talks today, everybody. Instinct Reasoning and Education, the Future of Trusted Autonomy. Dr. Robert Hunjet, who is Associate Professor at UNSW, but also a group leader in DST Group, and Dr. Iman, Associate Professor, Electrical Engineering at University of Melbourne. And there'll be two talks. The total time for the talks will be about 1 hour. And sorry, just trying to admit someone else here. With about 30 minutes for questions that we'll do at the end. So, and given we're a couple of minutes past, and I think we can make a start. So Rob, you're going to kick things off and I'll let you make a start.
Sure, thanks, Jason. So thank you very much to the TAS-DCRC for having us here. Iman and I have worked together on multiple projects for a few years now, and he's been collaborating with my team for a while. We're here today to talk to you about how we might actually move autonomy to the point where the behaviour exhibited by an autonomous system is trusted. This is the TAS-DCRC, Trusted and Autonomous Systems. And we argue that to basically get a system trusted, we need to make sure that we can provide some level of verification or some level of guarantees or assurance about the performance of the system. So what we'll do in this talk is we'll go through and suggest a framework which we believe is appropriate, and we argue must consider sensing, perception, control, and action, and look at actually closing the loop on these different parts of an autonomous system, and realizing and taking into account the interaction between them, and any perturbation within one may have a market effect on the other. We argue that for a system to be truly trusted, you have to be able to provide some sort of guarantees, or you'd like to provide some sort of guarantees on behavior, because that leads to that sense of understanding. Yes, it's not gonna move out of bounds, but I guess we need to be careful what we're asking for. Is asking something to be autonomous and something to be verifiable, are these actually conflicting things? So what we're going to quickly do is just touch on what is autonomy and how does verification appropriately apply. So I'll start off by asking you a few questions. This works much better in an actual room because I ask you to raise your hands and yell out and call, but just smile or shake your head, I guess, and I should be able to see. So firstly, which one of you has a driver's license? Does anyone have a driver's license? If you do, have you ever been in a car accident? Have any of you ever had a traffic violation? In the face of this, are you still able to drive? Does the government still say you're allowed to have a license? Do you take your most precious cargo, your family, and put them in the car in spite of the fact that you've had a traffic violation and you've been in a car accident previously? And do you think that given this, you would pass the V&V requirements that we would put on an autonomous car? I don't know about you, but I think I would fail miserably. And we really need to ask ourselves the questions. Are we comparing apples with apples? What is it that we're asking when we're saying we want a system to be autonomous? We're not saying that we want a system to be automatic, which is on the left of the spectrum here. It has very small system intelligence. A system which automatic system is a system which provides some immediate response to an input. I pull left on a remote control, the machine goes left, right? I pull a trigger, a bullet fires out of the barrel. These are automatic types of systems that they don't really do much for us, right? We move up the system intelligence and we get into autonomic systems. Systems as defined by Jeffrey Kephart from IBM, which is self-configuring, self-healing, self-optimizing, self-protecting. That actually sounds quite powerful, but they're constrained by the goals and policies that we put in place over the top of that system, and allows us to interact with them in a much more meaningful way. When we think about the definition of autonomy, and the true definition of autonomy is, I would contend, is self-governance. We're talking about systems which are able to learn and adapt and do things in new ways, but the learning can actually extend to the setting of their own goals and policies, right? So it's a very high level of intelligence and a very high level degree of control that we endow to these systems. So do we actually want a system like this to be verifiable, or do we want the behaviors that the system exhibits to be verifiable? And I think this is an important distinction, and we'll touch on it a little bit more as we move through. If a system is truly autonomous, and that means it should be able to respond to different things in the environment, and it should be able to learn online, right? If it's learning online, it's adapting the way that it performs. If it's exploring and trying to figure out within the state space how it should do things better, that can be relatively dangerous if it's not done so within acceptable bounds, right? So we have to constrain the way that these systems explore, but it needs to do it. And if it is going to do that, to try to give you a better answer or a better response or become further optimized, it becomes almost by definition non-deterministic, right? At one point you can poke it and it's going to have a reaction. You poke it again a few minutes later and it might do something different because it didn't like that you poked it the first time, right? Such a system these systems respond differently. And this means things like regression testing are not appropriate for systems of this type, right? I would say that when we try to put strict boundaries and strict controls on things, we're potentially constraining this ability to learn for a machine to try and explore new solutions to problem spaces. It needs to be done. So we need to have some loose boundaries, but they shouldn't be so stringent that they don't allow exploration. The other thing that we need to consider is that evaluating autonomy is a really hard ask, and developing autonomy is also a hard ask. We need the systems to work in unseen environments where there are levels of uncertainty in the environment. Right? We don't need a autonomous car to drive us down a beautiful straight road on a sunny day when there's no other cars on the road. We want it to do its thing and assist the human when it's raining, visibility is low, the kids are in the back screaming, and there's cross traffic coming across the road. These are when it's actually useful to a human operator. And if that system's trying to deal with uncertainty in measurements that it's taking in from the environment and what it's sensing, making any sort of action in the face of that uncertainty, we argue, introduces risk in the ability for the system to safely achieve the objective. And in the latter parts of this talk, my colleague Iman will talk about how we can actually introduce risk as a metric within how we look at optimizing performance. So how does one actually then go about training an autonomous system or making sure that an autonomous system does things appropriately, right? If we look at a sheepdog, a system which can act autonomously, but we can train it, we can get it to do tasks like herding of sheep, for example, right? Teaching the dog the basic commands to herd sheep and providing the dog with the ability or allowing the dog to learn that capability takes approximately 1 year. Right? And that a dog is a very smart system, right? In terms of if we try to actually implement in silicon the intelligence of a dog, it's actually a difficult problem. If we look at systems that are smarter, my two greatest creations, my little autonomous systems, right? The federal government mandates that I provide 18 years of training before I'm allowed to let them loose on the world, right? These are highly capable systems, right? My kids are able to learn new things, although they ran into the water with their shoes on initially, which is against all policies that we set, therefore proving that they are indeed autonomous, right? Evie and Sam are able to sort of figure out how they should approach things and do things, and they learn, and I need to train them for a long, long time. What we argue is that really the smarter and more powerful a system becomes, the higher level, the more capable they are of cognition, the longer it actually takes to teach them to do what that system needs to do, right? And we should actually embrace that in terms of taking on autonomy and utilizing autonomy, and look at how we actually teach humans. We look at teaching humans by educating them. And some work that we've done with Hussein Abbas and Sondas Osawar out of the University of New South Wales and Elena Petracchi from University of Canberra looks at how we can actually use the concept of education for humans and apply that towards the education of machines. Taking inspiration and noting that, you know, Elman back in the early days sort of showed that we can start by training systems to look at start training systems slowly and build up the complexity. He was able to train them to learn a language, right? We can start educating systems and providing curricula where we look not just at machine learning, which is the aspect of the machine learning something, the machine actually learning something, but look at machine teaching, where we try to figure out what is the best environment, what is the best set of environmental conditions to continually expose the system to, so that it learns in the most appropriate way and across everything that it needs to do. What this allows us to do is then test against certain qualifications and competencies and provide a competency-based approach for autonomy, as opposed to looking at saying, yes, this system is verifiable, keeping in mind that anything that is non-deterministic, you know, you're never able to, because the variance in the output to any input can be so large, you don't reach convergence. So you can't use these types of regression testing, right? So machine education, we argue, is a way to train a system to behave appropriately. And keep in mind that there are no constraints or bounds on how you as a human, a highly autonomous system, perform. Nothing stops you from swerving left on the road, right? It's just your education and your training and the fact that that's a bad thing to do and your understanding of that stops you from doing that. And we can endow computers and machines with the same type of approaches or the same type of ability. But I think we need to understand that humans and machines are different. If we look at Ian Goodfellow's work on adversarial examples, which I was extremely impressed by when Professor Scholes announced this to me years and years ago now, we see that a computer on the left sees a panda, but the computer classifier on the right, the machine vision classifier on the right, doesn't see a panda, given a very, very, very small perturbation that's been extended to it. Machines and humans see things differently. Similarly, a machine was able to learn how to play a game when the semantics of the game were completely masked or reversed, or the similarities were masked, using reinforcement learning, which was ontologically guided in the work by Dubby. This is something that they couldn't seem to get a human to be able to do in the limited timeframes that they had. Although they couldn't find humans willing to play the game for 100 years, right? So perhaps we could have done it, but we couldn't do it in the same sort of time frame for a simple task like this. Humans are very good at dealing with ambiguity in language, right? So when we think about machine education, human teachers follow pedagogical theories, which affords them freedom in the way that they operationalize the concept, which allows for adaptation to a specific learner's needs. Unfortunately, machines won't respond to that, right? Machines need formal definitions. If you give a machine ambiguity, you don't know what it's going to do. If I ask you to come into my office and take a chair, you're going to sit down. If we ask a robot to do the same thing, it might respond with, hey, where do you want me to take it, right? This ambiguity is not good for trying to get specific behavior for a machine. So what we can do is we can harness the formality. We can do the thing, we can embrace diversity, which is something that we've told to do all the time in the business world in our building of teams. Understand that a machine is good at formal systems and formal languages. So what might we do? We contend that using temporal logic type of constructs, which specify how a machine should actually behave and what it should try to achieve in a very formal way, is quite a powerful thing. And we've shown that we can build and evolve verifiable reactive behavior. And you can check these as you build them by using model checkers to ensure that what you're building is actually correct by construction. If you have simple reactive behaviors which are correct by construction, a machine and machine learning algorithms are able to operate on them to concatenate them in interesting ways to build more complex behaviors. And then you can teach the machine using education when it should instantiate which behavior, right? And wait for it, but a similar approach can be used for path planning, which is quite interesting. And Iman will talk about that a little bit later on as well. So We've shown in our work with Phil Smith, who I believe might be on the line today, that evolutionary computation approaches are able to create behaviors for specific contexts and specific tasks within a specific context. The work that he's doing now is working on showing how we can do that within the context of reactive behaviors that are verifiable. We know also through some of Phil's work that neural networks can be applied to environmental detection to figure out when we should actually look at instantiating each of these rules. Let's talk a little bit about reactive behaviors. If we consider a reactive behavior to be akin to the instinctual behavior of the human, I touch a surface, it's hot, ouch, lift my finger, right? We receive an input and we process it without actually holding state information. What we've seen is that such behaviors can be encoded simply, and they're actually good for explainability in terms of explaining what's happening, which engenders trust back to a human operator because of this transparency. Behavior trees are a potential candidate for encoding behaviors in this way. And in Oliver and Bazard's work, I think both of which, or Ollie might be at least online today, we've shown that we can actually represent behavior trees in a formal language like LTL without invalidating the concepts which make them powerful: flexibility, reusability, and modularity. That is, allowing a subtree to be verified by considering only that subtrees that are individual leaf nodes having a common interface so that they can be replaced, and modularity so that you can switch in and out behaviors at different parts of the tree. We've also shown through their work that we are, excuse me. I think I skipped through. There we go. This one here. We've also shown through Ollie, Bazard's, and Iman's work that we can create decision structures out of trees. And once we have these decision structures, which are a way of encoding the flow of a behavior or a composite behavior, we can actually identify specific modules within these behavioral structures, which allow us then to decompose the behaviors into smaller pieces and provide carry out the verification components using LTL and STL, for example, on only the small chunks, right? So if we want to change out part of a behavior, a composite behavior, we can do that as long as the new behavior that we fit in it adheres to the performance boundaries that were identified for that module. And the guys found that this could actually be found in polynomial time. It's a divide and conquer methodology because of this flexibility in the verification that it endows, and it allows for a plug and play approach in creating new behaviors. This work was inspired by a definition of a module and graph theory, and it's really a neat way of basically looking at how we can verify complex behaviors by verifying the sum of its parts. In a follow-on piece of work, the guys basically looked at how we could then take a decision structure and break it into a behavior tree, which allows for ease of representation and transparency again. And they found that there is an equivalence in certain circumstances if every module within the structure, so it has only one path which traverses all the nodes once and only once. So there's been a lot of concepts that we've just gone through. How might we actually look at implementing that within a model of cognition? I refer you to Marvin Minsky and his work on society of mind. He talks about an individual's cognition and the fact that that can be modeled by a multi-agent system. I want you to think of the cartoons you watched as a kid where a character was confronted with a choice, and you'd have a little devil that popped up on one shoulder and a little angel that popped up on the other shoulder. And one said, do this, and the other one said, nah, that's way too fun. That's way too boring. Do something else, right? Minsky's model is quite similar to that, except instead of just two agents, the devil and the angel, you can have a legion of agents which are telling you what to do. And each of these agents are able to take in various inputs and might be highly tuned for a specific type of behavior or a specific type of task, He's also shown that he could form composite behaviors out of this model by concatenating the performance of the agent, or concatenating the agents one after the other in a cascading type of fashion. And if it's done so in this manner, we can actually verify that that cascading behavior is correct. Minsky subscribes to the no compromise principle, meaning you don't take the devil's response and the angel's response sitting on your shoulder and merge them. You pick one or you pick the other, right? And this non-compromise principle, once again, allows for transparency. We see that there's a potential to use classification of the context to determine the behavior selection within an implementation of Minsky's society of mind. But when we think about what it is from the environment that we would want to classify to enable this decision to be made, we think about, well, it's got to be something about the similarity of the conditions for which the behavior was generated and for which the behavior was trained. So if you highly tuned behavior, trained under certain conditions, driving a car on a rainy day, then that behavior should be picked if the environmental conditions at the time match that. But there's also the concept of timescale for the operation. Does the decision need to be made in a quick time? Can it be more reasoned? Is it urgent? For example, planning a path from Adelaide to Melbourne, which I would love to do at the moment, but I'm unable to do so due to restrictions. Or is it about, still driving or moving from one path to another, but, looking at collision avoidance, which needs to happen arguably in a much faster time frame. Once we start thinking of these timeframes, we can see how these models of cognition, as the model of cognition as specified by Kahneman in his book Thinking Fast and Slow, really comes into effect. The fast thinking algorithm is something that the fast thinking part of the mind is something that makes decisions akin to instinctual decisions, but it may make mistakes. The slower thinking process works on the harder or ponderous tasks and works on much larger timescales. So what's really interesting is Kahneman talks about, that sense of no voluntary control. You drive a car on an empty road and you get to where you're going, and we've all had that moment where we just think, was that light actually red? You've driven on autopilot. You've had an instinctual behavior. What's really interesting is if you take that same behavior and try to apply it in the US, where you're driving on the other side of the road, this is far from instinctual, and it is quite a ponderous task. Kahneman also makes the point that a chess master has, the ability to instinctually make a strong chess move, where for someone like myself, that might take minutes, it might take hours to make a move of that sort of quality. So what this tells us is that you can train yourself for certain behaviors to move from system 2 to system 1 by repetition. And we find this quite interesting in the concept of machine education and machine learning, because the learning process itself and the training and the education process and being able to do things over and over again or think about how you might do it sits in system 2. But once you've actually mastered that and cracked that nut, it actually moves into system 1. The execution of a neural network is very, very fast. So how might we piece this together? Well, for particular contexts, we can see how reactive behaviors can be created and their system 1 behaviors. And by various means, whether they be generated heuristically via control strategies, rule-based systems, telereactive systems, or machine learning generated, we are able to apply logic to see what the behavior of those systems, of those small pieces of reactive behavior are actually like, and whether they conform to some sort of specification. And if they do, then that's great, because they are verified, right? We can then look at planning and reasoning type of behaviors, which can be created, as Iman will talk about shortly, sitting in system 2. And we can use machine education and classification type of approaches to allow the system to learn when it should actually specifically select an appropriate behavior at the right time. I don't think that society of mind or Kahneman need to exist separately, right? There's multiple ways of looking at putting them together. One that our latest conversations that Iman and I have been having, almost arguing in a friendly way about this. And one of the things that I think could happen is that we could have a society of mind model existing at each level of Kahneman's hierarchy. I think that this would be quite powerful because it addresses the scalability on behavior-based selection. So if you have your legion of agents, legion of behaviors, if you have an initial classification system which tells you about the time urgency and which system you should be looking at, you can then do the secondary classification on and the selection on a much smaller solution space. With that, I'll pass over control to Iman, or ask Jason to, please, who will provide some concrete examples of some of the things I've talked about now in approaches to addressing autonomy based on problems at different timescales in the face of uncertainty. Thanks.
Thanks, Rob. I'm going to share my screen again. Let's see. Here we go. Okay, as Rob said, that we are going to look at the problem from this Kahneman hierarchy point of view, and that really serves as an inspiration for implementing our own take on the autonomy stack. The way to think about it is we have a system that interacts with the physical universe through interfaces that we call sensors. And these sensors provide information at different rates and different qualities to different levels of decision-making, for lack of a better word. And the decisions that are made in the end are going to impact the environment. So the systems dynamics lumped together with the physical universe is the universum, and then the control actions impact the environment. Different types of information with different levels of granularity and quality. And then there is uncertainty everywhere. And each of these levels might operate at different time scales. Here I've drawn 3 levels, but that's a conceptual choice. I mean, there can be many levels, but there might be only 2. It's really a question, what is meaningful for each problem, really? The key takeaway here is that there are many interacting loops. All these decisions made in different time scales impact each other. So it makes the problem very hard. The other important thing to remember is we make design choices based on some understanding of the universe, and we don't want the choices to wreak havoc when what we assumed about the system doesn't agree with reality. So we call it graceful degradation of performance as we depart from the assumptions. Just a historic note here, this is closely related to the notion of cybernetics proposed by Norbert Wiener 70 years ago, and then Johnny von Neumann worked on it, Kolmogorov worked on it, and then in the 70s, Margaret Mead and Gary Bateson really started elaborating on it from an anthropologic point of view. But they called it second-order cybernetics. That's a whole different set of philosophy. The key is that all these systems interact with each other and they capture different aspects of a complex system. And what is desirable is just some hard formal guarantees of how the systems work. One point about Wiener that is good to remember, he nearly got a job at University of Melbourne, but University of Melbourne at that time was very anti-Semitic, so he went to MIT. Now, something that might be related to what we were discussing is, can the society of mind theory be considered in a cybernetics framework as well? The answer is probably, but that's the challenge is that how do we go and marry these notions together, which is a long story. Someone that I take inspiration in my research is Millis Jeffries, founder of MD1. He was crucial to the Allied war effort in World War II. And he has this famous saying that everything conforms to an equation if you only looked hard enough. So that's something I do. The other guiding thing, that the principle that I try to remember is, for example, is not proof, which is a Yiddish proverb. So we can show examples that something works out, but we really want certificates, things that we can rely on. Now, what is today's focus for the rest of this talk? I'm going to talk about 3 main strands of work. I will hint on other things along the way, and hopefully it would make sense. So I'm going to look at different systems that sit at different levels of the hierarchy. I start with control design for risk-based signal temporal logic specifications, which is something very ponderous in system 2. Then I go and talk about how can we integrate perception, decision-making, and motion planning as somewhere that sits in between. And then in the end, how can we design very fast, real-time systems that still give us some sort of guarantees? Is it possible? And what is the framework that we can look into these problems? So the first level is we want to have this machinery that takes uncertainty and captures uncertainty in a formal way. The second one is to have an integrated perception loop. And then we want to see what happens if the universum changes. The first bit, as I said, is the risk-based single temporal logic and control. It's a ponderous type of system. It belongs to system 2 and really wants to harness both the formal tools come out of STL or any other really temporal logic grammar. STL is more suitable here. And then really marry this notion of ambiguity in systems. Now, the first slide really sets the scene is planning and control as an optimization problem. I mean, any problem that you give me, I can cast it as an optimization problem. The question of if it is solvable or not is a different story, but I can always write it, but humor me for the time being. So many problems can be written like that. The theory allows us to guarantee notions of stability and constraint satisfaction and measures of mission success, etc. But these guarantees depend crucially on the accuracy of the models. And they are inherently uncertain. Something that I always teach my students is that an exact model doesn't exist, because otherwise it wouldn't have been the model. It would be the actual system. So that's something that we have to remember. Nothing is certain. So there is an inherent uncertainty. And then a note, again, in some of my other lectures when I teach about optimization, is the optimization theory and application is not the panacea to solve, to cure all of the diseases in the universe. And optimality on its own is not the goal. In fact, it doesn't really mean anything. I can select my cost function to be Rob is the best person in the universe, and it's trivially true, but what does it say about the system I'm trying to solve? It's a choice, really. What it does, it gives us a framework to understand solutions and try to bring different sort of mathematical perspective to solve potentially hard problems. Again, if you want to take one message out of this talk, my portion of talk is this. We just can't throw an optimization solver at an arbitrary problem and hope for the best. That doesn't work most of the time. So we have to be careful about how we go about doing stuff. Now, let's go back to that, what we were. I got sidetracked a bit, but let's get back to where we were. So we decided to bring uncertainty into it. So let's just introduce this W variable that captures uncertainties magically coming out of some distribution. But now we end up with an optimization problem that is ill-posed. How can we minimize a family of functions that are parameterized in something that is unknown and comes out of a distribution? And what do we really mean by optimizing or constraining in the presence of uncertainty? So that's the question we want to answer. So since guarantees only hold, we've already done that. So one way that we can try to make sense of things is to, okay, let's just take an expectation with respect to my W parameter, and then write the constraint in terms of the probability of violating the constraint or satisfying the constraints here. I want it to be larger than 1 minus epsilon. It is widely used. We call the constraint chance constraints. It is covered in many classical textbooks now. Alexander Shapiro's book is the best one if anyone wants to consult it. And but it has a problem. It is generally non-convex when you write the problems like this, and convexity is the watershed moment between things that can be solved, things that are not impossible to solve, and things that are very complicated. It doesn't quantify how bad is bad when we are not satisfying the constraint, because it says 95% you're going to satisfy it. But what happens in the 5% that you don't satisfy the constraints? So especially if these distributions come with long tails, fat tails, that's problematic. And in the language of risk analysis, it's an incoherent risk quantification. So what we propose to use is the axiomatic risk theory, which is the theory that underpins what I'm going to talk next. So axiomatic risk theory is something that came out of mathematical finance. It provides a risk measure, which is a mapping from the event space to extended reals. And we want the risk measure to satisfy a bunch of properties. Monotonicity of if an event is in some ordering is larger than another event, the corresponding risk should be larger as well. If we move the event to another point in the space, the risk should move in the same way. If I multiply it, the risk should be multiplied, and subadditivity. Risk of doing two things together is less than risk of individual of them adding up. So if I have a risk measure that satisfies all these four properties, we call it the coherent risk measure. In engineering, there is a lack of awareness, but people have started looking into it over the last couple of years. Now, I'm not going to go through all of these. These are the risk measures that a lot of people use. The first one is the expectation of something. The second one is some worst case behavior or variance. These top four are not coherent under the definition that I gave you. And these last two are. And I bet you that most of the time we only see these things. But while they are easy to grasp, but just looking at them, they don't carry the same set of properties that allow us to extrapolate from them. Now that's risk. I want to introduce you to another little notion, which is distribution and robust optimization idea. Now, evaluating risk measures require probability distribution. But in practice, we never have distributions. We can make assumptions, but we only have really access to data. So we try to use the data that we have to estimate or approximate some measure of distribution. So really, distribution robust optimization incorporates these sort of uncertainties that come into the system when we try to estimate the distributions as well. It is robust to all these little bits there. And in many cases, they lead to, I call them tractable-ish optimization problems. Again, I don't want to make grand statements that it always solves right. We end up with easy problems to solve, but there is a prospect for that. Now, just to see as a figure what distribution robust optimization really entails is classically we have a stochastic variable comes out of a distribution. Robustness really says the stochastic variable comes out of a bounded set. So we want to be robust with respect to all these elements of this set. Distribution robust says, okay, my variable comes out of a distribution, but the distribution itself belongs to a set of distributions. Now this set is called the ambiguity set. The ambiguity set come in different flavors. We can define them in terms of the moments. So I look at all the distributions with the mean equal to something and some covariance equal to something. That characterizes a family of distributions. We can use higher order moments. The other way of characterizing them is to use some measures of distance between distributions. So I'm interested in all the family of distributions, P, that are some distance away from some nominal P bar distribution, and that measure of distance is some epsilon that I pick. Now, the choice of this distance is non-unique, comes out of these different measures. But again, and each of them come with different interpretation and different meanings. And then the distribution risk measures are defined as the supremum of the risk of all these distributions inside the ambiguity set. So that allows us to now quantify the risk associated with the distribution robust framework. So what it starts hopefully making sense, we are proposing that we have to minimize the risk of something subject to the risk of violating the constraints being less than some parameter delta. It is far more sophisticated to handle uncertainty than what is currently available most of the time. Sophisticated always doesn't mean good, but at least it allows us to interpret things without relying on intuition. Especially intuition can really be deceiving when we deal with things that are random. Now, some of you might know about temporal logic, but I just quickly talk about it. Temporal logic came out of software engineering because they wanted to verify the behaviors of software, but around starting 20 years ago, early 2000s, people started bringing them into dynamical systems, as in physical dynamical system. Everything is physical. Things that move in the universe, which which came with the name of cyber physical systems and things around it. And this is just a framework figure out of Richard Murray's presentation 6 years ago in IFAC. Really, the idea is that how can we start using this sort of theory coming out of theoretical computer science and use them to synthesize behaviors or trajectories for dynamical systems. Again, a simple problem just to have something tangible. Traditionally, we can write a constraint optimal control problem, some measure that we want to minimize subject to the dynamics of the system and satisfying some constraints. That's what traditionally we used to do. But now in temporal logic framework, I still want to minimize some measure subject to the constraints, some dynamic constraints, and I want my trajectory to satisfy some temporal logic specification. And the grammar, again, if you haven't seen this, don't worry about it. It's really a way of writing propositional logic statements like and, or, etc., and combine them with things that are temporal. So I want always to do something, or eventually I want a certain condition to be satisfied, or I don't want this to be satisfied until this other thing is satisfied. So that allows us to state these sort of statements formally and rigorously. So it allows us to, just as a point of reference, mission specification for autonomous multi-robot systems. So examples are persistence monitoring, constraint ISR, complex swarm tactical maneuver. So don't engage area A until something in area B is satisfied. And then the specification will end up looking things like this. This is not, so for example, this means not always pi 3. So pi 3 should be violated at some stage. That's the statement that we want to satisfy. Pi 4 should hold until pi 5 holds. So that's the sort of language. So the notions of risk and temporal logic sit somewhere that are mathematically formal, yet readable by humans. It's not quite readable, but they are formal, and they are readable enough. That's already a big challenge of how to do the translation, but I'm not going to talk about that. It's really beyond my knowledge. Now let's bring uncertainty. I spun all this yarn to talk about uncertainty. Let's see what happens to uncertainty. So let's just, for simplicity again, just add them as additive terms. They perturb the system. It really doesn't make sense anymore to talk about satisfying the formula anymore, because the formula is a binary yes or no statement. If I perturb it, it wouldn't make sense. So we want to really quantify the risk of violating the specification. What is the risk of not satisfying the specification? Is it possible to do it in a systematic way? The short answer is yes. Again, I'm happy to talk about it, but I'm going to skip it. Really, the idea is that we can start applying this, defining risk semantics using axiomatic risk theory for dynamical systems, and apply risk measures to atomic predicates, and then from them build the corresponding risk measures for all the different statements in a grammar, in a temporal logic grammar. So we can build things recursively. So this allows us to transfer risk constraints to some tight and deterministic constraints by using the appropriate risk measure and bounds. And then we can rely on the rich universe of existing methods that try to solve these sort of problems. We have stated in our paper an explicit reformulation for distribution robust value at risk with affine predicate. So that's our concrete vehicle for stating what we've done. The general framework opens up exploration in many directions. Various risk measures and ambiguity set now can be incorporated. They just become elements of this. As long as they satisfy the properties that we like, they just can be plugged in. Nonlinear dynamics and predicates, they lead to non-convex problems. And then the challenge there would be quantifying the effect of approximation and convexification on the problem. And we can use other risk semantics as well. One big challenge later on is it possible to start looking at these problems over distributed systems? Because that's Here we can solve the problems for distributed systems, but we are solving them centrally. But is it possible to decouple them into smaller problems? Now, the next bit that I'm going to talk about, which is much shorter, is really about integrating perception and motion planning. It's a slow system. It's really system 2, but it sits between them. I use motion planning as a tangible example, but really whatever I say can be applied to whenever we want to move through any state space. So this is an autonomy stack that we are more familiar with. I have sensors that we know, actuators that we know as well, and then perception planning and control happen somewhere in between. Usually people just look at these elements separately without explicitly taking into account their interconnection and their interplay. And then the way that uncertainties really might play on each other. So what we did, we wanted to come up with a different way of thinking about it. So we wanted to, again, going using the risk accounting for different risks within and across layers in the autonomy stack, from perception to motion planning and control. The existing works usually don't adequately incorporate uncertainties. And even if they do, usually they make Gaussianity assumptions. And there's a good reason, because that makes the math easier. And I've done it before, but sometimes there is no justification for it. So we wanted to see if it's possible to say something else. So what we did was we introduced this output feedback distribution robust suffix to RRT star, which is a popular planning algorithm. And we try to incorporate these sort of notions of risk and explicitly incorporate SLAM errors, stochastic process disturbances, and uncertain obstacle motion and locations in the framework. So the main observation is OFDR RRT star grows trees of states, and really that's the key, and the state estimate distributions. It doesn't just grow states, it grows trees of distributions, how they lead into each other. And just to show you some moving pictures, the top one is not taking into account anything, just doing vanilla RRT. The second one is to use Gaussianity assumption on disturbances. And the last one is to use an ambiguity set. Of course, the last one is more conservative. And the reason for it is that we are looking at the ambiguity set that captures all the distributions with the same mean and variance. And that automatically incorporates a lot of fat tail distribution. So that's why it ends up being more conservative, because it wants to take into account for them and come up with something that minimizes the risk of violating the constraints in the presence of these fat tail distributions. And really, that's just the picture of how all of these things come together. So a picture, what we did was we had RT star, we had DRO constraints, and we did some low-level controller. We just used Kalman filter QR, but it can be anything else as well. It just, sometimes it's good to have a concrete example rather than everything becomes like there is a separation between divine and mundane. Sometimes it's good to talk about mundane things. Now I'm going to quickly mention another work that is a case of misclassification. When people are not careful, they might misclassify a particular solution as a slow problem, which in reality it's not. One example, major example that we came across is when we do minimum snap spline trajectory planning, which is something that's super popular whenever people want to plan paths for quadranters. They want to minimize the total integral of the fourth order derivative of the motion. That's the snap. Now, it just, again, something to remember. If I'm not careful and just write the problem as it is without paying extra attention to anything, the time complexity that I obtain in terms of the number of waypoints or segments that I want to connect together is exponential. At least it appears exponential. But if you are careful, it is not. So the triangle is what we have implemented. The blue one is just using the classic case of writing an optimization problem that captures the problem and just throwing a commercial solver at it, but it's a general commercial solver. Now, what this does, it allows us to incorporate dynamics of path planning in the perception loop as well. Because earlier people said, oh, these things are slow. So we do the planning without taking into account these sort of dynamics properties. Then we fit some polynomial that respects the dynamics. So this is just an example of what happens. This is the scenario of just coming up with a bunch of waypoints and then fitting a polynomial, which is a path, the orange path, which is ugly. This is the one. Now, if we bring in the machinery that uses the structure of the problem and just come up with a trajectory that is natively dynamics of which is nicer. But again, I mean, there are more things about it, but visually that's what it is. Now I'm going to finish up with the last bit of work that I'm going to talk about. It really talks about what happens on the fast system, and I call it running problems meet uncertain oracles. Hopefully it becomes a bit more clear. It's really the sort of family of problems that try to keep crunching numbers as the problem and the universe changes. Going back to this stack, the observation is everything changes, drifts, runs away from us. And there are different amount of information that is made available at different time scales. So we need to be able to have an handle over and make sense of what solutions we obtain by just in these sort of scenarios. So traditionally, if I have a problem and I want to solve it, I'm given a problem and then I extract information about the problem. That's what I call an oracle. It's an abstraction of telling me things about the problem that I can know. I feed the output of my oracle into some method and the method crunches numbers. Then the question is, am I getting close to some optimal solution or some point of reference? How far away I am from that point, and these sort of things. Now, but if the problems are changing, here I'm using time indices T and K to indicate the method can operate on a different time scale than the universe, and they can be actually in the same time scale. If my vehicle is traveling very fast, which as it's collecting information, it's the same rate that is computing as well. The change of the universe is the same rate as my computing step, or at the same time scale. So what happens there? What is the solution anyways in this scenario? So one thing is, okay, let's solve each problem completely. So formulate the problem, crunch numbers. That's what people, sometimes we can call them batch processing. So it is computationally expensive, and then we are not really harnessing new information that is made available to us. Option 2 is only run a small number of iterations in each loop and keep using new information. So really forego optimality for newer information to really get better understanding of what's happening. Okay, that's sort of the solution that we might be after. How can we measure the performance is the next question. There are different ways. One is a regret level, which is saying if I do this over some time horizon, and as if I was playing against a player that knew everything, an omniscient player that was always making the optimal choices, how much worse off I am compared with that player. So that's a regret. What is my regret over a finite amount of time? The other measure is the tracking error. How closely I am tracking the decision made by this omniscient player. So it really is a race against the universe. These measures really become really important in control and estimation type problems because we want to know if we are close enough to some desired behavior or not. Just a brief thing, what can we say about discrete optimization problems? Short answer is that in task allocation, assignment problems, we can, and I can talk about them later, but these are the references, but they come with different challenges. What happens if I have uncertainty everywhere? So my method is uncertain. What if my oracle occasionally gives me garbage answers? So that's another sort of problems that we have looked into to be able to get a handle of how this uncertainty really propagates in the whole loop. And then going back to the whole ambiguity set flavors, we cannot marry all of these things together. We can talk about I'm solving an optimization problem that has a parameter. That parameter comes out of a distribution. That distribution is drifting away by some measure of distance. What we did, we used the Wasserstein distance. It has a lot of, it's called the Earth mover metric. It has nice properties. And then what happens to my sort of regret measures using this data-driven type sort of methods? So that's something that we consider as well. Really, I mean, again, it's important when we talk about distributions drifting, sometimes we have this mental image that this distribution remains close to each other. Always they are in some vicinity, but that's not the case. They can drift. While consecutive time steps, the distributions are close under this measure, but over longer periods, they can get arbitrarily far away from each other. So where we started might not be where we end up. So we want to always be able, but we still want to use information along the path. So all of these things was made possible working with people who are much smarter than us and learning from them. So this is just a list. My major collaborations were with University of Texas at Dallas, Toronto, and then Antoine moved to Berkeley, and he's going to start an assistant professorship at École Polytechnique Montreal. Yeah, he was a visiting student at my group, and some people at KTH and Melbourne, and DST, UNSW, and University of Canberra as well. Now, just some summary to wrap up everything. We have shown approaches for addressing motion planning and control of autonomous systems operating on fast timescales, which is the instinctual levels, and planning approaches, ponderous reason based. An ensemble of these approaches is required to allow a system to operate in real world. For example, systems that solve similar problems at different timescales and different fidelities. We should always have them. We just can't rely on one. There are a lot of interesting problems in relating the current push in autonomous systems to existing fundamental areas, all this sort of cybernetics, for instance. And it's really gives us a large scope for philosophizing as well. Decision-making in autonomous system is, again, carried out in different levels. And it does not only timescales, there are different information levels, uncertainty levels, computing power levels as well. So there are this heterogeneity in different levels. There is a need for an integrated and systematic approach to autonomy, which is fairly obvious, but it's good to state it, that captures the whole sensing, perception, control action. And we just cannot dream up algorithms, blend them together, and hope for the best. So we have to be a bit more careful. And uncertainty should be taken into account in all levels, not just as an afterthought, and use the right set of tools for the problem that we are interested in. And machine education as a selection mechanism to choose appropriate behaviors across these different time scales is definitely something that should be investigated more. Again, thanks for everyone for your attention. We have time for questions. More than happy to take them.
Thanks very much, Iman, and also to Robert. If you'd like to just stop sharing your screen now, Iman, and we'll have people.
Yeah, no, I'm going to do that. Yep.
As necessary.
Yeah.
So we've got about 30 minutes, almost exactly, for some questions. I see there have been a few things have come up onto the chat, and we can go back and take a look at those questions. So let me start with this one from Kate, and I think there's been a little bit of to and fro with Rob meanwhile on this one, but noting here one of the limits of human reasoning for system 2 is the limits of attention, short-term memory, and conscious processing. Do we want to model human limits and fallibility in the way we design autonomous systems? Perhaps the advantages of distributed processing makes the relevant models more like insect communities rather than mammalian cognitive structures. So I wondered if Rob and Iman, perhaps Rob first, might like to make some comments. I know, Rob, you're pretty well entrenched in the small and many camp as well. So perhaps you'd like to comment first.
Yeah, sure. So, I mean, the small and many camp, I really like, as most of you know, a lot of my work's in swarming, which we haven't touched on here today because it opens a whole other can of worms. But you can almost think of the society of mind as a bit of a small and many in the agents that respond providing sort of different expertise or different ways of solving individual problems. I guess my response to Kate is that, yeah, I agree. I think that we can take advantage of the differences between humans and machines, and I don't think we need to in the learning process think that the machine won't pay attention, because we know it's going to, right? Where it gets really interesting, I haven't started typing because I don't know the answer, is what if we're using the machine to learn about a model of a human, and we talk about human-machine teaming? And then I do think, yeah, that those types of things that Kate's talking about definitely need to be taken into account to generate an appropriate model of how a human might respond to a machine during that human-machine teaming concept.
Well, thank you. Iman, any thoughts?
Just one thing is not making, as the computing hardware has become more powerful, we have to keep considering their limits when we design whatever system we are going to do. Sure, we have more memory, but there's a limit, and it comes with real cost in consumption of energy and all these other things that come with it. So it's important to be aware of that. Maybe we are scaling things up and down, but there is always a limit. That's one.
And I think what Iman's just touched on is something that Kate mentions later in the chat piece as well, and says, perhaps the taxonomy can assist with design decisions under varying processing and temporal constraints of the technologies. To which I agree, as Iman just has as well. And I think the definitions of what fast and slow are, is actually relative to those constraints and relative to the processing. But once again, taking into account and having proper models as things get more powerful is important, because what we tend to do is just be careless with the way that we throw problems at a machine because we think it's more powerful, and that's not harnessing the benefits of the additional computation power.
Excellent answers, thanks, gents. Perhaps this question here from Dean Philp. How does this model play with the idea of perception action feedback loop? The question really here is around embodiment. Dean says that it seems that embodied perception is the way we tackle uncertainty. I wonder if you might make any comment with regard to that embodiment question here, and how it appears in each of what you've described.
Yeah, okay, I'll give it a crack. So, I mean, I think that as humans, we definitely do. We see uncertainty and we deal with it as ambiguity, and the way that we deal with ambiguity as a human is basically just a gut feel, and that's great. I don't think we can do that whilst offering guarantees for a machine. I think we have to have one way of modeling what that uncertainty might be, so that we can then say something intelligent about how the machine might perform in the face of that uncertainty. And I think we saw that in Iman's talk with his ambiguity sets, and we saw that when the planning came through, there was uncertainty as to the position of the obstacles and the way that the machine was moving, so that we had less of an appetite, or the risk, maybe the appetite for risk, or the safety boundaries around the objects were larger because there was uncertainty there. So I think humans deal with it really well. I think machines potentially can, but not in a way that we would say, would adhere to the tenets of trusted autonomy. It's more about, suck it and see. It might be fine for a small little mini drone, but probably not so good for, like a scan eagle or something, a sky eagle or something like that.
Again, going to that, I think something is important one important factor to remember is what answer do we want? What question do we want to answer? If the question is, I have a machine, I want it to behave in a way that is not surprising, I have to define what surprising is. I have to define how I'm going to trust it. Without that, it just becomes, yeah, it looks good in this example, but I don't know what happens in the next example if I can't relate them together. I think it's really about what question we are trying to answer.
Oh, excellent. And I guess the whole thing with system one is this fantastic through that so much data, so much exposure to examples in the real world through the embodiment, that although it may not be explicable, generally it jumps to a conclusion, and it's usually right if you feel good about it. So there's that intuition thing which the military will very much appreciate. The coup d'oeil, getting the grip on a situation at a glance is the kind of skill that's built up. And would you trust it? Look, absolutely. But can I explain it? No way. It's not explicable because it's really not accessible to awareness in the same way. And so I think, the nice part about both of your talks today has been the embracing of both of those parts, formal guarantees, which in a sense, that kind of testing of what's happening in the world against, a specification is a formal way to do that, but there's an informal part which is potentially also really very, very strongly valid. Maybe I could ask for both of our presenters, are there any of the questions that follow, because there's a bit of a dialogue that was happening from here on. I could go to one from Tom Putland perhaps first, but then I'll get you to also take a look through them and see if there's any that you think you'd really like to answer. So the one from Tom Putland here is, how does the distributed robust optimization, I think is DRO, derivation of the worst case probabilistic distribution contrast to maximal entropy distribution given known parameters?
If I remember correctly, maybe I'm wrong, but whenever we talk about entropy and the family of distributions with some level of entropy, you can always write it as a Kullback-Leibler distance from a given distribution. So that becomes one instance. Again, I might be wrong, but I'm just answering out of. But that becomes one instance of the framework that I talked about. So we are saying, I'm looking at all these distributions with this maximal entropy. I hope that made sense.
Yeah, look, I think it does. So just kick in, Rob, if you want to comment. Any of the other questions that you guys would like to particularly take on?
I don't mind going through them. So I think Jason, pseudo Simon, you made that comment about, and you sort of just touched on it then, about instinct often being right. And I think generally it is. The thing about system two is that, you'd argue that system two would get it righter, right? So if you had more time and you had more processing power and you could just ponder and ponder and ponder and you weren't constrained by time, you get a better result. And I sort of talked about the example in the chat about an obstacle on the road, and we all know that the instinct is to swerve, and we've heard a lot of horror stories about that. It's the same sort of thing as, someone surprises you in a dark alley, and one of the things that most people do if they're not trained is, rather than hit the person, right, is they'll jump for fright. It's an instinctual response, which, if you didn't have the time constraint and you had more time and you could have system two override system one, you'd probably take it. That's what I was trying to say when, in terms of, it gets it wrong. It's not in relation to system two, given the same time constraint, system two would also get it wrong, right? It's just that we were talking about operating on different time scales there.
Yep. I understood.
There is a question by Kate as well, if there is a way of switching between 1 and 2 when we have measurable performance on level 1 and level 2. It goes back to, again, the question of what do we want to achieve? If for example, the measure of regret is translatable to something that makes sense, then we can use that threshold. There is no general rule of thumb, I say. It's really it goes back to this old question of when is close enough good enough? That's we can't answer it. It's we have to be specific for the problem, which is very valid, but it should be taken into account as a problem by problem scenario.
So maybe, is this a trigger also? I mean, I had a bit of a question here around the education component, because there's a bit there that kind of says the objective somewhere is saying it's not fitting with the world. And if the world was your set of constraints, your specification, that represents the world as you must have it, or the world as it actually presents to your machine, then is it really like saying, look, my concept doesn't work. I've got to change my concept of the world because it doesn't fit with the world. Perhaps you've reflected a little bit on the last part of your talk, Iman. Can you comment on that at all?
Again, it goes back to, sometimes I can have a perception of the universe that makes it is erroneous from the get-go. I can work within that universe, but if I haven't closed the loop of revising my perception, I am limited to make decisions within this erroneous framework. Right. But again, that's the importance of feedback and feedback in all these systems. I haven't covered it, but definitely a very important problem and a very, very hard problem. But that's for sure true, because if my assumptions are fundamentally wrong, I don't get anything meaningful. And as things drift away, these assumptions can shift, but there should be a mechanism that allows them to shift a long time.
Yeah, excellent.
A tricky one as well, right? It becomes about understanding when are we required to update our model of the world versus versus change the way that we're trying to control or action, because we take a step, we do something, and it's not what we expect. Is it that our action wasn't right, or was it that the model of the world wasn't right?
Right on. And I think that kind of gets to sort of Carl Friston's view of the mind in that one, as well as kind of two components, one changing itself and the other testing that through the world. And both of them are required at the same time. So there's kind of two simultaneous optimizations of a sort that are going on. Thoughts on any of the other questions here, guys? We've still got about 15.
I quickly can answer Daniel. I will send you a paper next week, so that's that, because he asked if there is a reference for the things I talked about. Tom's question, it's about how, if I quickly share my screen, here I was silent about how we are defining the ambiguity set. I mean, I mentioned I'll give you a bunch of different ways. Either you can define it parametrically using these first, second moments, and then some other measure of the support of the distribution, and look at all the distributions with these moments, which can be set by some parameters, and these other properties, they are symmetric, they have finite support, etc. Or I can capture it in a different sense of all the distribution functions that are some distance away from a known distribution. So the second way is a functional analysis type. So it's really all the mappings that live within some distance of a known mapping versus all the mappings that have these sort of parameters. So it's really, that's the freedom that we have in how we go about dealing with distribution robust scenarios.
Yeah, very
good. So I have a question, if I can butt in. Is that all right?
Please go ahead.
It was just a bit hard to type it all up. So I get there's a certain amount of uncertainty that comes from within a given probability distribution. And then there's the second bunch of uncertainty that comes depending on which probability distribution and which parameters you have picked for that probability distribution. So how do you constrain the possible sets of probability distributions that you're looking at here?
I shared the same screen. So the calligraphic set P is the set you're talking about, the family of distributions that we are looking at. There are different ways of defining them. The second way is really defining using these measures of distances to a known distribution. So I want all distributions that are some epsilon distance away from some known distribution P bar. Now, these measures of distances can be all these different versions of it. So that's one way of defining the ambiguity set, which is the set of distributions. The other way is to define it as all distributions whose, for example, first and second moment are given W bar and capital W. That's a different way of it's a freedom. The language allows us to define these sets however we want. Now, in the context of distributional robustness, then we have to be able to say something about this sort of, for example, the worst case risk of an event of all these different distributions. That's where a whole body of literature exists about how to solve these sort of problems over families of distributions. I can, if you are interested, I can point you to, I mean, if you'd like, there is a very good book by Bental, Alan Bental, Laurent Elgavi, and Arkady Nemirovsky. Excellent book. It's called Robust Optimization. The other book that I really recommend, is very, very good, is a book by Alexander Shapiro and some Russian name. I can't remember that name. So, but if you look up Alexander Shapiro stochastic optimization, you find a family of these sort of references, and the book by Bental and Elgavi and Nemirovsky, excellent book as well.
And so how do you decide where that cutoff point is for deciding whether to include a distribution in the ambiguity set or not? Is that kind of arbitrary, or is there a way of actually doing that accurately?
It's problem specific. Again, there is no general recipe for selecting an epsilon star that works everywhere. I can't, I mean, it's impossible for me to answer that.
Yeah, it sounds like a hard problem, yeah. That's why I was asking it.
Given a specific problem, you can try to design it so that you get the sort of guarantees that you're interested in.
Okay, thanks.
All right. Have any other questions here? I don't think so at this stage. So I could invite people if they want to, as Peter Smith just did, I've got a verbal question they'd like to put forward to Rob or Iman. Please come forward. All right. I think we might be about done, guys. So thank you both for a fantastic presentation. I always love the Kahneman stuff, and lots of thinking here about architecture of mind, if you like, and dealing with adaptation. I have to say, one of the things I find with people who are a bit naive to some of these sorts of technologies like robust optimization and control is people will say, well, you know, why would I ever want a machine or a weapon to be adaptable? Yet here, on the other hand, what this does, adaptability does potentially, is allowed to deal with far greater range of disturbances, and disturbances that are surprising in this sense. So it's reaching further and further to prevent failure rather than be some source of failure. And I think that's an interesting aspect of the motivation for these types of techniques. It allows these machines to deal with a far greater range and a spectrum of uncertainty than we could have normally ever dealt with by automation or as Rob described. So thanks again, everyone, for coming. And this has been recorded and will go up on our website, as well as the chat session. If there's anything out of session to answer, I'll ask the two presenters to write some points to that if they can. But thanks again, and have a fantastic day.
Thanks, everyone.
Thanks, everybody.
Cheers.
Thanks. Bye.